Okay, morning, afternoon, evening, everyone, for second day of our Peatier workshop. So I'm Ken Carslaw. So what I'll do is briefly summarize again for those who weren't here yesterday, the purpose of the workshop, and I'll also briefly update you on the main points of discussion yesterday. We had some very lively discussions at the end. In fact, we ran out of time, I think. So just a bit background on why we organized this meeting. So it's the recognition that there are two major things that we need to tackle in particular in climate model, but all atmospheric models together is model fidelity, which is how realistic the model is, but also reliability to make reliable projections, simulations, etc. And there are different views on priorities. A lot of people are pushing for greater model resolution, others are pushing for complexity. There are a lot of work going on meteorological ensembles, but also perturb-parameter ensembles. But perturb-parameter ensembles, I think, can make a major contribution to particularly the reliability, but they are seen by those who don't use them as, I think, rather too narrowly what they can contribute. So the aim of this meeting is to pull together the activities going on and ultimately write a short paper explaining the real value of this kind of research. So yeah, as we'll see in the presentations, people are using them to look at model responses and sensitivities, process level understanding, quantifying and constraining uncertainty, structural deficiencies, which is something that came up in a big way in the discussion, and also model simplification. So a lot more than just looking at parameters. So the aim of the meeting is to, first of all, showcase the range of applications. I think almost everyone working in this field is unaware of the breadth of work going on across different types of models and also different scales, from very fine scale cloud models up to the global scale. So we wanted to capture all that in one meeting. So you probably quite often go to a cloud meeting or a global climate meeting, but here we're trying to bring them all together, these different scales. So one of the aims is to share expertise on what people are doing, because a lot of people running PPEs are actually quite new to it, and there's a lot to learn from people who've done it before. And even when you've run it several PPEs like we have, there's still a lot to learn from other people, I can tell you. And also build a community of researchers, people with shared interest in this field. And then in the discussions, we want to scope out opportunities for development of this area, collaboration, some of that was already spinning up yesterday, and also how we can contribute to the grand challenges. And we would do that better if we were more coherent and agreed on what PPEs could contribute. So to do that, we aim to then write, as a result of this meeting, a perspective article to inform the community, which is something we would do in collaboration with WCRP. So just some reminders for online meeting etiquette. Please keep to time. I'll give you a 6-minute warning, verbal warning, and then please wrap up in 8. A reminder that we are recording, and this probably will go out to the YouTube channel, WCRP, in due course. There's an Etherpad, which was very actively used yesterday. So the link is in the program. Please use that. And remember, when you put something in the Etherpad, always put your name. So write, Ken, : and then your response, even after you've commented several times. It just helps to follow the discussion. And you can jump around in the Etherpad and make comments anywhere. Questions to the speakers are in the Zoom chat, but please don't just chat there. Use the Etherpad for chat and comments, wider comments on earlier presentations, just to avoid disturbance. And we have a WonderMe social area during the breaks if people want to join. I'm not sure how much that was used yesterday, because some of us stayed in the main room also to chat, but you can use that. A reminder also that if you're not presenting but you want to say something about what you're doing, there's an opportunity to share one slide later on in the discussion. So briefly, what happened in day one, if you weren't there? These are the things that were discussed. Obviously, you know which presentations were given, and there were follow-up questions, but these are the main discussion topics, which I think were very fruitful already. So structural error was something that was really highlighted, and I think this is something that's not understood by non-PPE people, if there is such a group, who think that we're just playing around with parameters, whereas a lot of work is actually going on to detect structural error. So that was a useful discussion. And it was pointed out that we should at least define structural error or non-parametric error, so that we can make progress in identifying it and then understanding the causes. There was a lot of discussion about linking atmosphere-only PPEs to coupled global model simulations. So the atmosphere only is very amenable to PPEs because they're faster simulations, but it's been found that sensitivities change in coupled simulations, and there's questions about how we understand the role of the ocean if we're building most of our PPEs on the atmosphere-only configuration of models. And then when we go to coupled models, how we select atmosphere-only variants of the model to run in coupled mode, whether they're representative. Multi-model PPEs were discussed, multi-model here being number greater than 1. So there's some where we only have maybe 2. There are others where we have perhaps 4 or 5 already in a multi-model PPE, MMPPE. So there's a small number of activities underway, but not in a joined up way across the community. And they're already revealing differences in sensitivities in different models. There's one PPE we're aware of where they're perturbing the same parameters, so they went to effort to perturb the same ones. But this is agreed not feasible for number of parameters more than just a few, because you wouldn't find common parameters across multiple models. So the other joint multi-model PPEs are PPEs of opportunity where they've been run and then they can be compared in some way afterwards. So these are considered a really fruitful way forward in understanding structural differences between models, for example. There's some discussion about how we feed PPEs, multi-model PPEs into the new CMIP design, which is coming up, CMIP 7. And we're encouraged to start discussion with the CMIP coordination to see how we could feed in. One option might be, for example, rather than building an entire full multi-model PPE activity in CMIP, we actually just submit equally good model variants that have been extracted from PPEs that groups have run. But that would require a change to CMIP 7 design, I think. Feeding into model development is a priority. You know, why are we doing all of this? It's really to improve models a lot of the time. So that should be prioritized. But I think the pathway through to model development is not so clear yet in a lot of the presentations, but it is seen as a priority. And then on the small scale processes, combined PPEs, for example, of large eddy simulations and single column models could be used to inform parameterization development, detection of structural errors, but there was not an obvious path through. So this work is at a much earlier stage in these sort of process scale models, whereas the global models have been run for a decade now. Multi-model PPEs in these small scale models would also be valuable for the same reasons that they're valuable at the global scale. But again, we're a bit further behind in that area. And we identified really considerable challenges in calibration, history matching, call it what you will, because of the initial condition sensitivity of small scale process models like cloud models, for example. We didn't discuss much, but hopefully we'll allow today a perspective article on the importance of PPEs in atmosphere and climate research. So we'll come back to that, but that is something that we're going to do. And I think there'll be lots of volunteers to help put that together. Okay, so that's all I had, I think, to say. Just to go back to the reminders, you find the link to the Etherpad in the program. Yeah, a new one for today. Okay, so if we're ready to go, is that everything, Leighton? Did you want to point out anything else before we get started?
That's excellent, Ken. Covered the bases.
Okay. So we will go to the first speaker, which is Minnie Park, which is PPEs of tropical sea breeze convection. Now, Minnie, if you want to share your presentation, good. I say I'll give you a warning at 6 minutes. Thanks.
Thank you, Ken. Oh. Yeah, good. Hello, everyone. So my name is Minnie Park, and I'm a postdoc at Brookhaven National Laboratory in New York. But today I'd like to present some of the works that I did in my PhD with my PhD advisor, Sue Vandenhever, and many co-authors. So today what I'm going to talk about is the PPEs of the mesoscale tropical seabreeze simulations that we conducted under two different aerosol loading scenarios. Just in case if you're not familiar with the seabreeze circulations, seabreeze circulation is ubiquitous and recurring coastal phenomena, and these are mesoscale circulations are induced by differential heating between land and ocean surface. And as you can see from the satellite imagery, you can see the signature of the sea breeze by looking at the inland moving or propagation of the cloud fields here. And especially in this case, there was a fire, and you could see how sea breeze redistribute the aerosols and initiate the convection as well. So with the increasing coastal population and anthropogenic impacts, the sea breeze circulation is one of the interests for many people to better understand and better forecasting. And here we got inspired by the fact the sea breeze forecasting remains challenging. And the major reason in terms of the modeling and forecasting the sea breeze is because there's huge uncertainty exists, especially in the initial conditions, because multiple meteorological and surface parameters and even aerosol conditions coexist, covary, and interact. So that's the motivations or why we decided to use the PPEs and emulators and multi-parameter space. So here are the list of parameters that we perturbed for both for all the aerosol conditions that we considered. So here, as you can see, these parameters are again initial conditions of the sea breeze simulations, and we considered different aspects and boundary layer structure and the intensity in terms of the temperature and humidity. We also consider the inversion layer strength and depth and wind. So these white colored parameters are atmospheric parameters. And we also consider the ocean and land parameters because these are important for the surface heat fluxes, which are a major source of the mesoscale circulations. And these atmospheric parameters are more relevant to the convection, moist convection. So we use we perturb these 10 parameters using the Maximin, Lead, and Hypercube sampling method. I think a lot of people mentioned that yesterday. So we created the 130 parameter combinations, and we used the same combinations for the clean or control and polluted scenarios for our purposes. So here is our summary, PPE summary, and I'd like to note that two PPEs that we use in this study are already published, one in JGR, which for the control simulations, and comparing the control and polluted PPEs are recently published in the ACP. So if you're interested in, here is the citation. So the purpose was for the first work, we were more interested in quantify the relative importance of the 10 different parameters that I showed you on the sea breeze characteristics, as well as the convective intensity. And then we we added another sets of PPEs and the polluted scenarios for the second purpose, which is to examine the enhanced aerosol impacts for the same characteristics for the sea breeze characteristics, as well as the convection particularly induced or associated with the sea breeze circulation. So we use the regional atmospheric modeling system, or RAMS, and this is cloud resolving, or this was used as a cloud resolving mode. And the domain was quite large, as you can see. And for the horizontal resolution, we used 1 kilometer, and we had 57 vertical levels, and it was stretched from 100 meter to 1 kilometer near the modal top. As I showed you already, we perturbed 10 parameters, and because we had 2 pairs of these simulations, so we have a total of 260 simulations, and the training runs were 100, and the validation ones were 30. I'm not going to go into the types of parameters because I already explained. So it was 10-minute output, and each simulation was 24 hours, and the delta T was 3 seconds. The related approaches is Gaussian process simulations, which also a lot of people mentioned yesterday. And again, like to mention that we have 2 PPEs, one for control and 2 the second one for the polluted, and like to note that the aerosols we perturbed here is mostly sulfate, and these aerosols are microphysically and radiatively active in our simulations.
6 minutes.
Yep. So I like to briefly go into the results. So this is control and polluted, and this is what's plotted here is the variance based sensitivity analysis, and this the output variable here is the median updraft velocity, which in our simulations are representative of the updraft velocities of the convection ahead of the sea breeze, which are mostly driven by surface heating. And by comparing the control and polluted results, we found the soil saturation fraction is most important parameter for this boundary layer mixing and updrafts. But when with the enhanced aerosol loading, it became the relative importance of the soil saturation fraction became less important with the enhanced aerosol loading, and with the results was pretty robust. And another thing, in terms of the dip convection associated with the sea breeze front, we had a very sharp transition as a function of one of the parameter, which was initial boundary layer potential temperature. So in the control simulations, the output variable here is the maximum updraft velocity, which is indicative of how the sea breeze initiated convection, how strong it was. And because of this sharp transition at the 297 Kelvin in control simulations, we were only able to build the emulator around this range. And in the polluted case, the value was a little higher at the 299 Kelvin. So because of this, we couldn't use the emulator for this the maximum updraft velocity. As you can see, these orange box 2 variables are deep convection related output, but as you can see, like these 2 red dots are the deep convection simulations, which are kind of outliers because there were only 12 simulations out of entire 130. So the emulator struggles. So we use the emulator for the limited ranges. So we didn't use the emulator prediction beyond this ranges. Just want to mention that. And to kind of briefly summarize, we found that the robust changes or suppression of the convection, and it was represented or shown very clearly in the variance-based sensitivity analysis, but when we compare the control and polluted. However, as again, the deep sea breeze initiated convections are sort of outliers in our PPE. So we had to extend these studies without involving emulator, and we added more or reran the 12 simulations in two different aerosol conditions by turning up the aerosol radiation interaction. So these studies in preparation for the manuscript. So yeah, and I think I should stop here. Yeah, thank you.
Okay, thanks very much, Minnie. Maybe time for one quick question from someone. Can I ask, do you see a path through to model improvement, or are you trying to at this stage just understand the processes?
It's more the understand the processes.
Okay.
Yeah, instead of the model improvement. Yeah.
Okay. Yep. Thank you. Okay. So next up is Annika Oertel.
Yeah, I'll just try to share my screen.
Extratropical cyclones.
Oops. Can you see the screen? I'm press full screen mode.
Yeah, that's good.
Okay, perfect. Yeah, thanks for the opportunity to present our work here. So we primarily want to use the PPE to better constrain cloud microphysical uncertainty in extratropical cyclones to primarily improve the process level understanding, but also to better constrain potential error growth in numerical weather prediction. So we are using the ICON model in global configuration, and we also include 2 refined nests that are focusing on our extratropical cyclone case study, and these nests are run in convection permitting resolution. We perturb a total 5 parameters related to microphysical processes and also sea surface temperature. And our data is output hourly for the 3 days of our cyclone case study. We further use online diagnostics and online trajectories, and these online diagnostics significantly compress the information that we actually want to extract from all the simulations. So specifically, as I mentioned before, we are looking at an extratropical cyclone case study, and we are particularly interested in the coherent airstream that leads to the formation of this characteristic cloud band and also the associated surface precipitation. In numerical weather prediction, this is also important because the ascent behavior of this airstream can influence with the upper level jet and degrade the quality of the weather forecasts downstream. And the ascent behavior is strongly driven by latent heat release from cloud formation processes, such that in that synoptic situation, the uncertainties from cloud microphysics can potentially propagate to the larger scale flow. And we use the Lagrangian perspective to identify this coherently ascending airstreams. So the key questions that we address is which uncertain microphysical parameters influence the trajectory ascent behavior, surface precipitation patterns, cloud structure, large-scale flow, and so on. And here I want to focus on some recent results on trajectory ascent behavior and surface precipitation. So I said most of the information about our simulation setup already. I just want to show that the convection permitting nest is actually focusing on the cloud band here, and we are further using a 2-moment cloud microphysics scheme in our simulations. So the online diagnostics that we have implemented, we output diabatic heating rates from individual microphysical processes. And with that, we can actually quantify how the parameter perturbations change the microphysical process rates and also hopefully identify some compensating processes. And we further integrate these diabatic heating rates along online trajectories that are run online in each of the simulations. And that is very useful to characterize how the perturbations influence the trajectory ascent behavior, but also to quantify which of the microphysical processes most strongly contribute to the total heating of the strongly ascending airstream. So a bit more details about the parameters. So we perturb direct microphysical parameters, which are the capacitance of ice and snow, and also the maximum supersaturation used in the saturation adjustment scheme, CCN and INP concentrations, and also sea surface temperature. So sea surface temperature primarily perturbs the specific humidity in the lower troposphere, and this is often very poorly constrained below this large-scale cloud band in numerical weather prediction, but it has the potential to strongly influence the entire ascent behavior. So this is primarily meant to actually be a source of initial condition uncertainty for theta E in the lower troposphere. And like a lot of other presenters already before, we use Gaussian process emulation and subsequent variance-based sensitivity analysis to quantify the different sources of uncertainty. And with that, I want to show some first results of how the perturbations influence the trajectory ascent behavior. So we can characterize this overall ascent behavior of the airstream by computing a characteristic ascent time scale of each trajectory ascent, and then just plot a distribution of the ascent timescales for each trajectory for each of the ensemble members. And this is now shown here, where each histogram shows one ensemble member, and the members are colored according to the degree of sea surface temperature perturbations. And we can already see that if we increase sea surface temperature, we in total get a larger number of ascending trajectories, so enhanced mass flux. We increase the mean ascent timescales, and in particular, the fast ascending trajectories are increasing in number, and we also change the convective fraction that is embedded within this airstream. And for all these diagnostics that I've now mentioned, we built a Gaussian process emulator and quantified uncertainty contributions. Now the overall red colors here now show that the overall trajectory ascent behavior is most strongly influenced by our sea surface temperature perturbations. However, we also have some smaller contributions from the microphysical parameters. And this now also changes or influences the surface precipitation pattern in the extratropical cyclone. And we use different diagnostics that quantify the time domain integrated surface precipitation sums, but also the precipitation efficiency. And I want to start with the surface precipitation sums. So the overall dominance of the red color again shows that the total time domain integrated surface precipitation is most strongly influenced by by changes to sea surface temperature. In particular, if we integrate over 3 days, so that's the entire life cycle of our cyclone, sea surface temperature is the only source of uncertainty, and we can understand this as this airstream is very efficient in picking up all the available low-level moisture, transporting up, which eventually rains out. However, if you look at shorter integration timescale of a day or 1.5 days, we see that the microphysical parameters become more important, and this is related to changes in the precipitation efficiency that actually leads to a delay of surface precipitation. And with that, I want to continue with the sources of uncertainty for the precipitation efficiency. So we define different diagnostics that quantify Lagrangian-based proxy for precipitation efficiency, but also the classical Eulerian-based microphysical precipitation efficiency. And we see the overall dominance of CCN concentrations, such that if we increase CCN, as expected, we significantly decrease the precipitation efficiency. And this impacts actually the precipitation structure. So what is now shown here are system-centered precipitation composites. So we're always centered at the evolution of the cyclone. And the black contours here now show the composite precipitation for our reference simulation. And it basically reflects this elongated cloud band that leads to precipitation mainly ahead of the surface cold front located here. And the colors now show difference between high CCN and low CCN members. And what we see here is that if we increase the CCN concentrations, we decrease the precipitation efficiency, which leads to a downstream shift shown here in blue of the surface precipitation relative to our ascending system. In contrast, if we decrease the CCN concentrations, precipitation efficiency is higher, and that leads to more precipitation in the region where precipitation is already very large, directly ahead of the cold front, which leads to a local intensification of the surface precipitation. So based on this, we can conclude that although the total precipitation sums are most strongly influenced by the low-level available moisture, the aerosol concentrations and the precipitation efficiency strongly influences the spatial distribution and also the local surface precipitation intensity. And with this, I'd like to leave up the summary slide here and just want to mention that we find that the trajectory ascent behavior and also the precipitation sums are most strongly influenced by sea surface temperature, which can potentially influence also the downstream ridge amplification, which may be important for numerical weather predictions. And we also find that the microphysical parameters are very important for the detailed precipitation structure and the local intensity. And this is just some very first results that I've been showing, and we want to dig a lot more into detail and also look at the detailed cloud structure, in particular, including ice formation processes, because we think there are a lot of compensating process rates in the model. And we also want to analyze the radiation balance, potential vorticity structure, downstream flow evolution, and so on. Yeah, thank you.
Sorry, I had trouble unmuting myself. Thank you very much, Annika. That's really excellent, really interesting. Lots of things going on there. Any questions?
Can I ask a question, please?
Yeah, go ahead.
Hi, Annika. That was a really interesting talk. I guess you're focusing a lot on the processes, but of course, right in the early timescales. But I guess you know, SSTs, for example, are going to be affected by the microphysics parameters in longer runs. So I wondered if there was any plans or a way, or whether someone else in your organisation had perturbed the model on longer timescales. So you aim it run just to see what the impact might be on surface fluxes or something like that. I suspect everyone's struggling to do coupled models yesterday, as we were discussing yesterday. But to actually get a handle to see if how the microphysics might feed back on and change those SSTs or
yeah,
things like that.
we haven't done that so far, and I think we also do not have specific plans to run it on really substantially longer time scales than what would be used in numerical weather prediction. What we think is that we significantly change the surface fluxes, and I think if you would run the simulation for even longer, that would become the dominant impact, just simply because we consistently increase the moisture. That would eventually lead to an amplification of the ridges, and that propagates downstream, and I think that would significantly change the entire simulation. Whereas the cloud microphysics, and as you've seen, when we look at longer timescales for a surface precipitation, there the details are less relevant, because often in extratropical systems, the air streams are very efficient in picking up everything that is at the lower troposphere. Yeah, I hope that partially answered your question.
Yeah, thank you, Annika. We can probably pick that up again in the discussion. Some important points there. Thanks very much.
Thank you.
So the next speaker is Hui Su, and it's on deep convection and subtropical clouds, also dynamical.
Okay. Thanks. Yeah, I'm Hui Su. Thanks for inviting me to speak here. So this talk takes material from my collaboration with Kathleen Scarrow, Yuan Wang, Feyaza Mate, and David Neenan. This is the summary of our PPEs. We use the CAM5 of CESM1 with perturbations of 4 convective parameters and 10 cloud microphysical parameters. Each run is 10 years driven by observed SST. We output monthly data. So this table shows the parameters we perturbed. The top 4 were convective parameters, and the next 10 were cloud micro and macrophysical process. You may refer to the papers for details of the parameters. So the motivation of our studies is to better understand the driving factors for the intermodal spread in cloud feedback, particularly the low cloud feedback over the subtropic oceans. We all know ECS, the climate sensitivity, is primarily contributed by low cloud feedback. But actually, based on the CAM5 PPEs, we hypothesized the model diversity in deep convective parameters drive a large fraction of intermodal spread in low cloud feedback. We have identified 3 pathways, namely the temperature stability pathway, moisture mixing pathway, and the radiation subsidence pathway. So in this chart, each layer corresponding to a PPE in which we perturb deep convective parameters. And the y-axis is the low cloud fraction average over the descent region, or the changes of the low cloud fraction per degree of surface warming. So an x-axis are lower troposphere stability, the moisture contrast between boundary layer and free troposphere, and the large scale subsidence. So you can see when we perturb deep convective parameters, it creates a large spread, and that actually influences all those local cloud controlling factors, namely the lower troposphere stability, the moisture contrast, and large scale subsidence. So guided by those PPEs, we turn to CMAP6 model simulation and look for the process if we see in the PPEs, if they are present in the CMAP5 multimodal ensemble. So in particular, we look at this radiation subsidence pathway that were not actually discovered before. So in this scatter plots, each colored dot is a CMAP6 model simulation. The differences is the end of century mean minus the beginning of century mean normalized by tropic mean SST. So the left panel shows the magnitude of tropic high cloud fraction change per degree of warming is highly correlated with the tropic ascent area change. And the middle panel shows this ascent high cloud fraction change is also highly correlated with the outgoing long wave radiation. And the third top panel shows the outgoing long wave radiation change would actually corresponding to the large scale subsidence rate change. And in the models, when subsidence rate change, you will see differences in the low cloud fraction change under warming. So that corresponds to different low cloud feedback and climate sensitivity. So basically the relation we found is a tightening of tropic ascent area under warming leads to a more decrease of tropic high clouds that enhances atmospheric radial cooling. So that corresponding to a less weakening of large scale subsidence. And in the models, less weakening of large scale subsidence corresponding to greater reduction of low clouds, so higher climate sensitivity. So in this chart, in the top panel, you can see those insets are the CAM5 PPEs. So they actually shows a very similar behavior to the multimodal ensemble from CMAP6. So in the CMAP6 analysis, we also found another pathway, like the mean state stability could influence the subsidence rate change under warming. So on the right, like on the top, you can see this mean state subsidence rate is highly correlated with the large scale subsidence rate change under warming. And then in the model, this mean state subsidence rate is actually correlated with the occurrence frequency of heavy precipitation indicated by monthly mean precipitation greater than 10 millimeters per day. So we turn to CAM5 PPEs to better understand the origin of those model diversity in the static stability. So in the on the left, the top chart, the different numbers corresponding to convective entrainment rate in the CAM5, with larger number corresponding to a higher entrainment rate. So models with a higher entrainment rate actually is associated with a weaker large-scale static stability and a higher vertical velocity. And a higher vertical velocity is associated with lower, fewer low clouds. So that relation is consistent with what we saw in the CMAP6 multimodal ensemble. And this entrainment rate relation to the static stability could be understood by the cloud precipitation onset statistic shown in those colored shaded figures. So when the model has a very low entrainment rate, the convection, like a convective onset, more easily to occur. So the mean static stability could be rather high. But for models with very high convective entrainment, the convective onset is less likely to occur. So the mean state static stability needs to be high. So this actually is insights we gained from this PPEs to tell us actually what could be potentially origin for the multimodal ensemble.
6 minutes.
Okay, so furthermore, I want to show you actually different types of PPEs actually could give up different insights of circulation cloud interactions. So remember, we have two types of PPEs. In the convective PPEs, we perturb deep convective parameters. And in the cloud PPE, we perturb the cloud microphysical process. So here I'm showing you the high cloud fraction change versus the tropic ascent area change. So you can see in these two types of of PPEs, their relations are opposite. In the convective PPEs, because we directly perturb deep convection, so that actually influences large-scale circulation, so that then modulates the high cloud fraction. But in the cloud PPEs, we actually perturb cloud and cloud radiative effect directly. That feeds back to large-scale circulation. So in this case, when you weaken the cloud radiative effect, the tropic ascent area, or the ITCZ, becomes wider. So it's opposite relation to what we saw in the convective PPEs. So in summary, so we actually learned a lot from the PPEs with the perturbations of convective parameters. Particularly, we found this radiation subsidence pathway in the CAM5 and also existing in the CMAP6 multimodal ensemble. And we also found the convective entrainment is a key parameter that determines the mean state static stability and regulates the large-scale subsidence rate change under warming. And the convective and cloud PPE reveal different aspects of the circulation and cloud interactions. So lastly, I want to point out, because our analysis so far are based on correlations between different variables. We are still doing like a mechanism denial experiment to really modify certain process so we can pinpoint the exactly physical mechanism to establish the causal relations. We are also actually use observations to constrain the model simulation, identify which parameters actually will be more realistic. So thank you.
Thanks very much. That's very interesting. We like the link to CMIP. That's what's coming up in the Etherpad. Any particular questions on this talk? You can put it in the chat or put your hand up or just switch on your mic. There's something going on in the Etherpad. Anyone want to raise that question?
Sure, I can.
Yeah.
If there's time, can you elaborate a little more on your mechanism denial experiments? How would they be set up and what would be the outcome?
So for example, like we found this like a ascent area change, basically the weights of ITCZ is highly correlated with the high cloud fraction. So we still want to understand how the actual circulation change is influenced the high cloud fraction. Is just setting a large scale bound. So we actually want to modify the process. Actually, we could change the large scale ascent change. For example, the water vapor shortwave feedback appear to be an important process influence the weights of the ITCZ. So we actually modify the process like a water vapor, the shortwave sensitivity. And also I think SST pattern, so like how the SST gradient is could actually influence the large scale circulation change. So we actually also imposing different SST patterns. So look at the circulation, then the cloud's response.
Okay, thanks very much, Hui. That was very interesting. So let's move on to Lauren Marshall. Jumping into volcanic eruptions, I believe.
Okay, can you see that all right?
Yeah, we can. Thanks a lot.
Excellent. So I'm going to be talking about some PPE work that we've done to look at how eruption source parameters affect volcanic radiative forcing and sulfate deposition. And so here is the summary of the PPE. The model we used was UMUKCA, so that includes the HADGEM climate model. We run it in atmosphere only mode, and we're really focusing on interactive aerosol modeling so that we can simulate the evolution of sulfate aerosol following an eruption. I think the main thing to highlight then is the number of parameters, which in our case was 3, which is, I think, quite a small number compared to some of the talks that we've seen already. But what's nice about this is that we can actually start to visualize this in 3 dimensions. And so I want to show you some of the things that we have done in the rest of this talk. And those 3 parameters included were the amount of sulfur dioxide emitted by the eruption. the eruption latitude, and then also the emission altitude. We looked at 3 years for each simulation, and this is so that we can capture the kind of evolution of the aerosol and the radiative forcing signature. We then went on to emulate this. We've done some sensitivity analysis and then also some history matching in terms of constraining the types of eruptions that might lead to an observation or the like, and I'll come on to that. So the main question was really, how do these different eruption source parameters affect the climate response? And this is because the amount of SO2 injected dictates the amount of sulfate aerosol that can form, but there's some non-linear effects as you get to large SO2 emissions because particles coagulate, they are less efficient at scattering radiation, also fall out of the atmosphere more quickly. Depending on where the emission is, depends on whether it's constrained to one hemisphere or perhaps it's spread globally and might have a large response, and then also the injection height. So there's been a few studies that have looked at these parameters on their own, but we kind of wanted to disentangle the contributions and look at whether there were interacting effects. So this is our design. This was Latin hypercube sampling across the 3 parameters that we looked at. And each one of these triangles indicates one of the simulations that we conducted. The red ones are the training runs, and then we also had an additional 11 simulations for validation, which is shown in black. And so it's plotted against the value of latitude, the injection height of those emissions, and then the size indicates the emission. And so we looked at emissions between 10 and 100 teragrams. This is between the size of Pinatubo and onto Tambora and beyond, so an order of magnitude there. Latitude across the whole globe, and injection height focusing on emissions in the stratosphere. So this is just showing the results of what the radiative forcing is in each of those simulations. And so again, each triangle indicates a simulation, and because we've just got 3 parameters, we can plot this in 3D quite nicely. And so it's plotted against what the emission height was, what the latitude was, and the SO2 emission, and the color is showing the integrated radiative forcing, hence why it's in megajoules per meter squared. So that's over the 3 years of simulation. And just by looking at this kind of 3-dimensional scatter plot, we can start to see how some of the parameters affect that total radiative forcing. Radiative forcing is higher for eruptions that have the larger SO2 emissions, and higher for eruptions in the tropics. So yeah, we can start to see some of the patterns. We then went on to emulate this. And this is the result of that emulation. So we've now been able to fill in that space. And what we now get is we can predict the radiative forcing for any of these eruptions, and then we get this continuous model output, and we can start to pick out some of the features, or we see more features in this emulated surface. So there's some curves in the response here. We find an interesting impact of injection height, in which case the larger radiative forcing is actually for eruptions with the middle injection height, which then tailors off above and below that. We then went on to do some sensitivity analysis. I won't go into that detail, but the results are that the SO2 emission is the most important, followed by the latitude, with injection height having the least contribution to that variance. One of the other things we went on to do with this work was to actually look at sulfate deposition. And this is because there's a large uncertainty in kind of reconstructing past radiative forcing, because so many of the sulfate spikes in ice cores are from unknown eruptions. There's a spike, we know that an eruption must have occurred, but we don't know where it was. And so when we set out to do this work, we wanted to think to look at whether we could constrain the properties. Could we find out what the eruptions were? And then we were able to predict the radiative forcing better, since the SO2, the latitude and the height affects that forcing. And these plots are showing what the simulated average Antarctic deposition was in the simulations. And so we have higher values of Antarctic deposition for, again, larger SO2 emissions as you would expect, but also for eruptions that are closer to that ice sheet, and the same for Greenland.
6 minutes.
Thanks, Ken. And so in the same way as I showed you for radiative forcing, here is the emulated deposition, which again just kind of brings out those features more strongly. And now we can start to constrain this. We can start to find the eruptions that might lead to a measured deposition constraint. And I've just got a little video here that shows this. So this is showing our 3D cube. And then pulled up here is what the emulated Greenland deposition is. And so we can see stronger deposition for eruptions in the Northern Hemisphere and for the higher SO2 emissions, with a not obvious relationship with injection height here. We've then got some nice little sliders on this tool that we can constrain. So this is saying what eruptions would match a Greenland deposition of around 40 to 80 kilograms. And then we can apply additional constraint, which is an Antarctica deposition. So that was between 24 to 38 kilograms of sulfate. And what then is being shown is what the radiative forcing is of these eruptions that have been left. So we're really lucky that we can kind of show this visually in 3D. And what we can see is that we're left with actually quite a large range of different eruptions that meet those two constraints that I've just put in here. And if we focus on just one example for Tambora, this is if we hadn't known that it was from Tambora, we can see that to match both of these constraints, the emission has to be greater than 80 teragrams. The eruption has to be in the tropics to meet both the Antarctic and the Greenland signals. But what's interesting and what's shown in the colors is what the radiative forcing is that there is a range in radiative forcing. So there's quite a large number of eruptions that can meet those constraints. And this is important because, coming back to the fact that loads of the signals are unidentified, is that we find that this is the case for most of them. So we've looked at 8 different unidentified signals here. Includes 1230, 1815 as an example of if it hadn't have been attributed 266. For each of those cases, there is a large range of consistent eruptions. We followed this through. I can't go into the details now, but in terms of what this means for uncertainty in the temperature response, and we find that this leads to an uncertainty of 1 to 2 degrees. And this is a problem because this uncertainty is not accounted for, and there could potentially be quite different radiative forcings of these past eruptions because of that uncertainty and how different eruptions could match those ice sheet signals. So to summarize, we've used PPE and Gaussian process emulation really to explore how these parameters affect things like radiative forcing and sulfate deposition. Our sensitivity analysis really demonstrated that the SO2 emission is leading that. But we've then been able to do some quite nice things with constraining these emulators to match constraints, not just sulfate deposition, but finding eruptions that might lead to a particular AOD or a response that's 10 times greater than Pinatubo or things like that. And our final conclusion being that many eruptions are consistent with these sulfate deposition patterns. Thank you.
Great, thanks very much, Lauren. There's a couple of questions in the chat already. Maybe we could just deal with them really quickly, if you would. From David Sexton about the circulation and the importance of the QBO. How was that accounted for?
Hi, Lauren. That was really interesting talk with a really nice output. I was struggling to pick up all the details because this was so new to me, and I was wondering about how much noise there was in your samples. And that noise I was thinking might come from like circulation changes and how the different circulation might vary where the aerosol goes in the forcing. So I kind of think Jim Hayward wrote a paper saying the QBO phase might interact with tropical volcanic eruptions and that might affect the forcing. So I wondered if you could comment on that, please.
Yes, definitely. QBO will impact that kind of initial dispersion. So that effectively is another parameter, and we did not explore that. So for each of the simulations, they had the same initial conditions. They were simulated during an easterly QBO, similar to the QBO at the time of Pinatubo. So it's to try and keep that consistent. I think that's a really interesting point. I think this was started off as an exploratory study. We chose 3 parameters to keep it simple, but I think in the future, looking at QBO would be another nice thing to add, and would add to some of the variants in, like you say, the forcing and also the deposition.
Great.
I'll put a comment.
Thanks very much. Let's take, sorry, David, let's take that into the Etherpad. I think there's an open question about how you deal with something that is either one phase or another. You'd have to repeat the whole PPE, but maybe take that into the Etherpad. Okay, let's move to our final presentation in this first session. Oliver Wild. I think we're shifting into chemistry. Yeah, another topic. Thanks, Oliver.
Thanks very much indeed. Say good morning, good afternoon. Let's get this full screen. There we go. So yeah, we're looking at here at studies we've been doing, looking at sensitivity analysis and our first attempt at calibration of a global chemistry transport model. So our focus is really on atmospheric composition and ozone in particular, but oxidation processes in general in the atmosphere. A quick summary of the kind of situation setup we're looking at. I'm using a global chemistry transport model for looking at the troposphere and focusing on gas phase processes, roughly 2.5 degrees resolution globally. And we're looking at 36 parameters that span a wide range of different processes that affect oxidation. So rather than just choosing a particular set of processes or chemistry to focus on, we're bringing in emissions and deposition processes and meteorological processes where possible too, to try to get a kind of holistic view of what the sources of uncertainty in atmospheric composition simulations are. We're mostly focusing on monthly variations globally, but we're also output a lot of data at hourly resolution from these simulations. So there's a lot more things that we can look at in future. And we're focusing really on a single year of meteorology, 2001. So there's an little issue of different years of meteorology might affect the results differently. The processes we're using are very similar to those described at other times during this meeting. We're looking at Gaussian process emulation and variance-based decomposition to look at the sensitivities. A slide of motivation, first of all. A couple of different metrics that we're looking at. One is the tropospheric ozone burden, which is the total mass, the annual mean mass of ozone in the troposphere, somewhere around 300 teragrams, but different model studies have quite a wide spread of different results for this. And I've plotted it off on the left against the tropospheric chemical lifetime of methane, which is basically a good metric for oxidation processes in the atmosphere. And again, there's a big variation over different model studies. So there's a large model diversity in the kind of simulations of these metrics, which has persisted for the last 10 or 15 years. We're not really getting any better at this. And I've marked off the best observation-based assessments of these different metrics, and many of these model studies lie well outside that range. And on the right-hand side, the other focus is on surface ozone. And again, models capture the general seasonal behavior of ozone at a variety of different sites, but there's a lot of spread in the models that we really like to kind of get a handle on and understand better the processes which are causing these variations, this uncertainty. So we this is the second generation PPE we've done. We've did a kind of feasibility and exploration a few years ago. I wasn't going to show this, but I brought it up because there was discussion yesterday about multi-model PPEs, and we've had a lot of success with application of this type of simple PPE across different models. So in this particular case, we were just simply looking at emissions processes, deposition, and a couple of meteorological variables. And we're using eight parameters and about 80 runs. And I twisted some arms for colleagues in GIS and at NCAR to contribute to this study too. So if you look at the tropospheric ozone burden, so looking at the kind of posterior distributions across this 8-dimensional parameter space, the distributions for tropospheric ozone look really quite similar for the 3 different models here. In the lower row, I'm showing you the sensitivity indices, so the contributions to the variance from these different sources. There's a little bit of difference between the models, as we might expect. The CAM-CHEM on the right has a much greater sensitivity of ozone to lightning NOx emissions in the upper troposphere. But on the whole, the general contribution from different processes looks quite similar in these models. So we expect the overall behavior to be fairly similar. In contrast, if we look at tropospheric methane lifetime, which is really giving us a measure for OH in the atmosphere, we see really quite different behavior across the models. The distributions are different shapes, and they're shifted along the axis quite substantially. We're getting quite different values for the methane lifetime. And if you look at the sensitivity indices at the bottom here, big sensitivity to the different surface emissions, but what drew our attention particularly is the differences for atmospheric humidity, which is a key driver key source of OH in the atmosphere, and in particular that the GISS model has very low sensitivity to humidity, and the other 2 models have much higher sensitivity. So again, we're starting to understand why the model chemistries are different, and this has substantial implications for climate, thinking about what happens to methane lifetime in future. With the GISS model, we'd expect it to increase, and with the other 2 models, we'd expect it to decrease. So there's substantial implications of this. Moving back to our new PPE, we tried to explore a much wider range of processes involving meteorology and deposition as well as chemistry. The one thing we can't quite get to yet is differences in model structure, but that's something that I'll mention a little bit later on. So we're looking across a wide range of different processes across the model. And I'm using here just the UCI chemical transport model. So basically, we can start to identify what the key sources of uncertainty are. There's a handful of them that jump out as really important, particularly some very simple kinetic parameters, particularly the rate constant for NO2 and OH, which has been studied for 30 years or so, but we still don't have quite good enough handle on it. And it's really important for
6 minutes.
Thank you. For the ozone burden, for the methane lifetime, and for surface ozone. So we run a 280 runs with this model across these different parameters. If we look at surface ozone in a variety of places in different parts of the globe, these are the sensitivity analyses by month. And what's comforting here is they make sense in terms of what's driving the processes driving surface ozone in these different locations. In more remote locations, it's very often deposition processes, whereas in the more polluted places, it's hydrocarbons, often VOC in wintertime and isoprene in summertime. So we can identify what the key uncertain parameters are, the key drivers of uncertainty. And deposition to water often jumps out as the largest single uncertainty. So clearly, this is a process that we need to characterize better in our models in order to be able to reduce the overall uncertainty. Our attempts at constraints, we say focusing here on ozone. So what we've done is we've taken the tropospheric ozone assessment report, the TOR surface ozone climatology, which has brought together ozone's measurements from across the globe for the last 25 years or so. And we're also looking at an ozone song climatology, which gives us ozone at about 5 kilometers altitude in the atmosphere. So we're using both of these two together on a monthly basis to try to constrain our model uncertainty. And so we're using a Monte Carlo approach, a Metropolis Hastings approach, to try to get close to basically trying to identify which sets of parameters are really quite reasonably close to the observations. So if we look at our kind of an example here of our posterior parameter distributions, the scale here 0 to 1 is just the normalized uncertainty over the full range of uncertainty in each of the parameters. The model, the control model is roughly should be at 0.5, right in the middle here. So basically, it's telling us that we get some kind of constraint on deposition processes, which should be a little bit faster in the model, and we get a little bit of constraint on the emissions processes, which should be a little bit less. But we get actually rather little constraint on photochemistry, which is somewhat disappointing. We're hoping to get a bit of a better constraint on that. What's particularly interesting here is if we just use the TOR surface data to constrain our model, we get a set of results like this. We plug those into our full CTM, we run it, and we get very good comparison with surface observations. But if we look at what's happening higher up in the atmosphere or in the global ozone burden, we find the results look terrible. So this is one reason why we started to use different sets of observations. So if we do the same thing with 5 kilometer data from ozone sondes, we get a much better comparison. So we're clearly getting quite different information from these two different sets of observations. And I think clearly there's a structural error here associated with what's happening close to the surface of the Earth. So we've started to identify what's going on there. We're not able to be specific about what that is, but clearly there are some unknown unknowns, so to speak, that we're not dealing with properly in our model. So to summarize, it's been a very interesting and useful type of exploration of sensitivity. And it's been quite useful for identifying what the key processes are that we need to understand better. But there are substantial challenges with how we apply observations, in particular the kind of representativeness and scales appropriate for both the model and the observations, something that Jill was mentioning yesterday. And how we deal with structural errors is a key uncertainty too. But there are certainly new opportunities here in terms of how we might use different sets of observations, in particular for different chemical species, and bring them together to constrain these things better, and then ultimately to apply to different models. So thank you.
Thanks very much, Oliver. Maybe time for one quick question before we move to coffee. I don't see anything in the chat. I put something in the Etherpad, and maybe just a comment that your model seems to suffer from a lot of equifinality, like our aerosol model. Would that be a correct statement?
I think so, yes. I think probably we've been rather over ambitious trying to constrain the whole thing at once, but it was an interesting experiment to see what, how it goes. It's useful. I think calibration is a little bit, true calibration in a proper sense is a little bit beyond us, but it is still it has been extremely informative. Yeah.
I think we maybe bring back in the discussion how we deal with equifinality, error cancellation, and also you pointed to structural errors. I think this is something we're all grappling with. Anyone who's done anything like you've done there, and we've done with aerosol and etc. So I think that's something where we need some progress, because we're kind of stuck now to make progress on that. It's good that you highlighted these things. Okay, thanks very much, Oliver. Thanks all to the speakers so far. I think we break now for coffee or tea or dinner, whatever it is, wherever you are in the world. It's 10 past. I suggest we do keep to a 20-minute break rather than cutting it short, unless Ben or Leighton think otherwise.
So that's fine. I would just encourage you to all come over to Wonder Me. It does work very well, and yesterday we had some nice unexpected conversations that can come up. So if you're unsure, then do come over. Okay, thanks. And so let's meet at half past whatever hour you're on, and we'll see you back here on Zoom.
Ben and I'll both chair the second one, but with him leading. We have 5 presentations in this session, and they cover all of the key aspects that Ken outlined this morning, the summary from yesterday. They're largely focused on global climate models, but they do cover those key aspects that we're hoping to include in our perspective piece. So again, I'll give a 6-minute warning, and please keep to 8 minutes. Any questions in the chat, and carry on using the Etherpad. That's been really good so far. So first up is Ken. So when you're ready, Ken.
Yep. Thanks, Leighton. You see that okay? Okay. Yeah, I'll keep this quite short, but I wanted to bring it in really just to cover the breadth of everything that the meeting was going to cover. This is work we did as a PhD student at Kamalikas and Gupta. It was a sort of a PPE of sort of just exploratory, really, of the secondary organic aerosol problem. And we didn't get around in the end to emulating it or anything else, but it did reveal some interesting things, and I'll share that with you. So we using the GLOMAP global aerosol model, so this is a global chemical transport model using the same aerosol scheme that's in our UK climate model now, 100-kilometer resolution. We were perturbing 6 parameters, and we did 60 simulations with the intention of emulating. So they were designed with the Latin hypercube. And they're all parameters related to secondary organic aerosol production, which I'll briefly introduce in a moment. We ran for a year and we looked at monthly mean output. And what we did is use skill scores against aerosol observations. So we mapped those out across the parameter space. Rather than looking at model behavior, we looked at model skill in reproducing observations. So secondary organic aerosol is, for those who don't know, is created from the oxidation of precursor gases, which come from biogenic and anthropogenic sources. It's really important because it accounts for about 50% of the submicron aerosol mass over continental regions. And it also makes a major contribution to cloud condensation nuclei and is therefore important for clouds and climate. And it's a problem of huge complexity. One of those problems where there's way too much complexity to put into climate models. So the schemes for secondary organic aerosol tend to be hugely simplified. And some groups have tried to sort of get a halfway house with some complexity. So there's always the question of how much complexity do we need, and could we actually demonstrate the utility of that complexity against observations? Or does the model simply suffer from compensating errors? So that's what I'll show you here. So the number of compounds, the reactions, the range of volatilities, which controls how these compounds then pass into the particles, are all hugely complex. Thousands of compounds and reactions, and potentially dozens of volatilities bins as well. So we need to simplify that. So we were asking, could aerosol measurements be used to constrain the uncertainty in such a system? And could we identify the most important processes that could be treated in large-scale models? So just to introduce the way we've set this up, it's a 6-parameter scheme for secondary organic aerosol. The way it's done is that we have 3 classes of volatility. So extremely low volatility compounds come from oxidation of monoterpenes from vegetation, and they can only partition into the nucleation mode here on the left. So that affects particle formation. Then we have what we call low volatility organic compounds. And this is an accepted way of visualizing, understanding organic compounds in the atmosphere. They can partition into all of the particle types, Aitken, accumulation, coarse, etc. And then there are semi-volatile, which partition partially into these particles, but not entirely. And they have different sources from the chemistry, both from biogenic and anthropogenic. So this is about as small a scheme as you could wish to have in your model, other than simply lumping it all together and saying, we produce some organic compounds that partition. This is sort of like the next level up. And we wanted to test whether this could even be discriminated and constrained against observations. So we use aerosol measurements from around the world. And we're going to show you comparisons with total particle number. That's all particles. Particles larger than 50 nanometers diameter, which we get from size distribution measurements. That's a kind of a proxy for cloud condensation nuclei. And then the total organic aerosol mass. And you can see the global distribution of these measurements, mostly over land, inevitably. So if we simply line up the PPE members according to particle number, you can see we span a huge range from simulations that have hardly any particle number all the way down to bottom right with huge concentrations. So somewhere in here is reality. It's probably somewhere in the middle. The top left simulation has way too few particles and the bottom right has way too many. So we could definitely constrain that. But what would it constrain in terms of the 6 parameters? That's the other question. If you arrange them in the same order, but now show particle concentrations larger than 50 nanometers, you see that it's not so obvious the order. It's particle number is nicely ordered. Particles larger than 50, you see, for example, bottom right, that some of the parameter combinations that give you very large total particle concentration don't give you a large number of CCM. Okay, so, and then you get some up here which have large numbers of particles larger than 50 nanometers, even though they had low total particle numbers. So constraining one will not immediately constrain the other, and there is something to be learned by working out how these observations constrain these parameters. So I'm going to jump into showing you the Latin hypercube distribution of these in all these sort of pairwise comparisons. So this is one of the parameters against another one of the parameters, and each one of these squares is one of the parameters against another parameter. So they're all the two-dimensional visualizations.
6 minutes.
So that's 6 minutes. Yeah. So first of all, what we're showing here is skill score. We're not showing the behavior of the model. We're showing the skill versus those observations, which is something we'd never done before simply with the PPE members. So for example, you can see that the most skillful models are mostly in this corner here in terms of mass. So if you produce too much vapor and have too much production of these compounds, then you can see the skill is very low. Okay, so that's a general conclusion, that this really does constrain the mass budget of secondary organic aerosol, at least some of them. But you see, for example, in this one here, for the anthropogenic and the semi-volatiles, there's no constraint. The skill is pretty much equal across the parameter space. But for some of the compounds, we can get a constraint, which is nice. If you now look at it for number larger than 50 nanometers diameter, you see quite a different distribution. You see a blue stripe down here. So that particular parameter is unskillful if it's low. And what we find is that there's another part of parameter space in top right here, which is really skillful for these two, the extremely low volatility and the low volatility. So we can find a part of parameter space that's skillful for particle concentrations. But if you look at the general pattern, the distribution of these two, you see in general they mismatch. The unskillful models for organic mass are actually the skillful ones for particle number. So this reveals a structural error. This cannot be reconciled by finding a part of parameter space that's good for both. Okay, they seem to be opposite to each other. So that even without building an emulator, we've been able to reach that conclusion. So yeah, 6 parameter SOA scheme, secondary organic aerosol scheme, is underdetermined. So even though we've only got 6 parameters, we find very different combinations of parameters produce equal skill. So you would not be able to distinguish them, in which case you probably shouldn't have 6 parameters. You should probably have fewer because you can't demonstrate it any better. Best simulation was a compromise. It's not particularly skillful at any of the 3 variables. So we learned that the model probably has structural deficiencies. Best simulations for mass are the worst for particle number. And we can say that the solution would probably be more primary particle emissions. You can't find a part of parameter space that simply adding more secondary vapors is going to get you the right combination. We also, I didn't show, but had a large seasonal bias, and we could fix that with a temperature dependent production or wintertime primary emissions. So it's nice how even a simple study like that can begin to point towards structural deficiencies, a bit like Oliver showed before. But we definitely would have been better building emulators and could have been more conclusive about some of these things. Okay, I'll leave it there.
Thank you, Ken. There's no questions in the chat, but there is one on the ether board you might want to comment on. David is asking, what value did you use for the LVOC? Go ahead, David.
It's the parameter that you ended up having to make the compromise on. I just wondered whether you ended up on the left side to favour the organic mass or the right side to favour the CCA.
Somewhere in the middle. We can say that somewhere in the middle is about the best. But as I said, it's not the best parameter combination for anything. It's the least worst, let's say. So we need quite a bit of the extremely low volatility, and quite a bit of the low volatility will give you a reasonably good model, but it's not the best model. If you want the best model for any one of those 3 variables, they're in different parts of parameter space, basically, which is suggesting structural errors.
Ulrika, I can see you've got your hand up, but you might have to put your comment in the Etherpad. Ken, if you could stop sharing, and we're going to welcome Ben Yang to share his screen.
Okay.
We can hear you, Ben.
Yeah, it's
come up now and it's in presentation.
Okay.
That's great.
Okay.
When you're ready, Ben.
Okay, thank you, everyone. Hello, my name is Ben from Nanjing University. It's my special place. I'm very happy to have the opportunity to introduce my recent work about using the PPE. So the title is Understand the Timescale Dependence of Global Energy and Precipitation Response to Potential Cloud and Convection in an SGCM. This work is done with collaboration with Zhun from IAP, Yoko from NGO, and Yun from PNL. So the main summary is in this table. As I mentioned before, the purpose is to understand the time scale of climate response. We have 16 parameters and 256 simulations. The main feature is we use the short-term PPE to reveal the connection between the fast and slow responses. The main motivation is that the cloud and the convection are important but highly uncertain in climate models. So PPE approach is widely used to quantify these uncertainties. However, when perturbing these cloud scale processes, the atmospheric states may respond much slower than clouds do, which can in turn affect clouds. Finally, the system will reach a new equilibrium, which makes the model response highly dependent on timescales. So the question will be, how do these responses change with timescale? Answering this question will help better understand the cause-effect relationship among different aspects in the climate systems. To address this question, our objective is to investigate the dependence of climate response and understand the physical relationship between fast and slow.
Ben, you've paused there.
Follow show most important parameter, the responses and their change with time. So our work is mainly based on the short-term PPE, in which each member has 12 simulations for each month of the year. The simulation was integrated for 6 days, so we can let the atmosphere nearly reach its equilibrium at the end of the simulation. The model we used is the atmospheric component of FGOES, and we investigate 16 parameters related to cloud and convection. We use the QMC sampling method to generate 256 parameter sets. Before do any analysis, we conduct some running averages so that the sample size increases for longer time scale, which helps to reduce the noise due to natural variability. But I will first focus on the global mean energy and precipitation responses. This figure shows the intermember correlations between simulations on different days with their counterparts on day 60. So the earlier the R-square exceeds a critical value, the faster the response. From this figure, we can know that responses of clouds and their relative effects are much faster than that of precipitation and turbulent fluxes. If we add these two variables and we have the new variable, which means the net gain of radiative and sensible heat in the atmosphere, NGRS, and this variable together with the latent heat flux as well as the precipitation, these 3 variables are balanced with each other at the end of the simulation because of the conservation of moisture and energy. So if we take this pair, for example, we can plot the lead-lag relationship between precipitation and NGRS. The diagonal means the contemporaneous correlation between these 2 variables, and in the left up section, this means the NGRS leads precipitation. We can find several interesting points. First, the correlation is close to 1 at the end of the simulation, which means 2 months are almost sufficient to reach a quasi-equilibrium for global mean analysis. And the equilibrium solution of precipitation is highly correlated with the response of NGIS during the first several days of simulation, which means we can use the fast response of NGIS to constrain the slow response of precipitation in climate models. So what are the most important processes responsible for these variations? We use the variance analysis to understand this problem, and this different color and different pattern indicates different parameters, and the x-axis means different time scales. For NGIS, the variation of parameter impacts is very weak, and microphysics is always the most important parameters during the whole simulation. But for precipitation, deep convection is the most important at the beginning of the simulation, but then microphysics dominates the precipitation response, follow the parameter pattern of NGIS, while for latent heating, the microphysics is the most important at the beginning, but then the microphysics dominates. Although deep convection become less important at the end of the simulation, they are still the most important ones for the partitioning of precipitation and is important variation. So one can ask why. So we checked the results and found the convection have some offsetting effects on long wave and short wave radiation. Then I will quickly show some regional results. This plot is about the correlation between precipitation and NGIS as a function of day and latitude, which means there's a very weak relationship between these two variables. So precipitation has to be balanced by the heat transport and the local heat storage. Because the local heat storage is very weak at the end of the simulation, so heat transport is the most important, which means circulation plays an important role in energy and moisture balances at regional scales. So we take the northern hemisphere Amazon region as an example to further understand the relationship between fast and slow responses, and we can see that the fast response of NGIS can explain about 50% of the slow responses of monsoon precipitation. But at the end, both NGIS and the transport term are important for precipitation. So in summary, we use the short-term PPE to understand the time scale dependence of the climate response. And for global mean results, response of clouds and their effects are much faster than that of precipitation. So we can use the faster response results to constrain some slow responses, which will save the computation resources. The response feature and its convergence is a function of latitude, and the circulation and transport play important roles at the regional scales. In the future, we are going to focus on the response of regional climate extremes and climate variability at different scales, and also the fast slow responses in LC coupled system. Thank you for your attention. That's all my talk.
Thanks very much, Ben. There's a question from David, which you're welcome to ask yourself, David, if you'd like.
Thanks. Hi, Ben.
Hi, David.
So, as I understand, you're going to be making a PPE couple model soon, and your last period kind of implies that. Do you think your relationship between NGRS and the precipitation will hold once you couple it and once the SSTs start changing?
I think it will change because we are now looking at the NGS in the atmosphere instead of those at the surface. So I think there will be some difference. But this work is mainly focused on the slow response means the atmosphere scale. So the slow and fast, the definition of slow and fast response will be different when we using a coupled model simulation. Thank you.
Thanks.
So if you could stop sharing for us, Ben, that'd be great.
Okay.
And
Okay.
I'd
Yeah.
like to welcome Zhun to share when you're ready.
Yes, thank you so much. And I will share my screen. Okay, can you see that?
Yeah, that's clear.
Hello, everyone. It's a great honor to have this opportunity to share our results. Today, I will introduce our PPE project and also some preliminary results. Maybe I should turn off the camera to make the connection better. We are using the latest generation climate model developed by the Institute of Atmospheric Physics. And it has 3 components. The first one is a great atmospheric model and also the ocean model. And we know that the PPE provide a way to systematically but efficiently examine the parameter sensitivity in a very complex system. And also famous institute already done that, like Met Office and the DOE. But for the IP model, our model, so we are still in the beginning of this beginning stage in this area. So we try to do with a PPE simulations. And here is the design and methodology and the motivation of our PPE. This slide shows an abstract of our PPEs. Our PPE generally has 4 steps with different scientific objectives. The first one is 80 years multiple parameter PPE. And based on this one, we carry out a short-term PPE and 40 years long-term AMIP PPE. So after that, we will conduct a fully coupled model PPE with the same configuration and the parameter settings. The sampling approach, we are using Monte Carlo sampling approach, and we are using the general linear model to investigate the parameter sensitivities. Next is the configuration and the motivation for each phase of our PPE project. Because it is the first time we do the PPE, we actually know very little about the parameter performance. So in the first stage, we perturb as much as possible. We selected 34 tunable parameters from deep convection, shallow convection, micro and macro physics, and turbulence. And we generate 1,000 members with 2 degree and 30 levels model simulations. Also, we use 2 different initial dates to start our simulations. They are totally 80 years. Also, we want to know the spin up of the parameter uncertainties. So we start another simulation. We reduce the parameter from 34 to 16 based on their sensitivities. And we use the TA map and we use the TA map project to initial our PPE studies. I think Ben already introduced that, so I will skip that. Also, because we are focused on the climate model, focus on the radiation, precipitation, and especially the East Asian summer monsoon. So we know the climate is very complicable, and they have so many climate variabilities. So we'd like to know whether the conclusion we obtain from the short-term and the mean state PPE are still consistent with those we found from the long-term PPE. Also, more important, we want to know how do the parameter affect the climate variability and the interaction of the physics processes and the circulations. So we did 40 years PPE simulations, and we have outputs the monthly and the daily results. Here comes some very preliminary results. this slide shows the spatial distribution of the STD of some very important Moisson variables in response to the parameter perturbations. We can see that relatively large variance occurs over the Moisson regions from the Indian, East Asian, West Pacific, and also the tropic. That means our PPE can be used for the Moisson studies. So now we want to check the contribution of parameters to the global mean precipitation. We divide our samples into 8 bins for each parameters. And for each bins, we can get the mean value as shown in the box. And we can also get the variance as shown in the bar. The parameter, the number here means the relative contribution of each parameters. If it is red, that means the contribution is very significant. You know, because the global mean precipitation is a result of the energy balance. So those parameters affect the energy balance have the greatest impact on the precipitation, such as the microphysics parameters, like the order conversion size threshold for the ice to the snow, and followed by the cloud macrophysics, like the relative humidity threshold for the cloud fraction, and then the convective parameters. So this is a spatial distribution of the parameter contribution. We found that the result is quite different from what we get from the global mean. And at this moment, the contribution of convection become much more important, especially over the Moisson region and the tropic. And the macrophysics really works on the high latitude. Also, the macrophysics works on the stratiform cloud regions. So that means the Moisson is maybe the result of the interaction of the convection and the large scale. So to investigate that, we use the Wang and Fan index to describe the interannual variability. It's generally the share of the zonal wind between the West Pacific and the warm pole. So it actually can be regarded as an index of the subtropical high. So the green line shown here is our members, and the black line is reanalyzed. We found that the PPE sample have a very huge spread here. That means we have a very different impact. So how to understand that? If we use the two sample tests to score the Wang-Fan index and the simulation and the observations, we can score our simulations. And we will use GRM to investigate the parameter contribution to the score. And we found that the evaporation efficiency is the most important parameters here. We also pick out the top 10 simulation with a high score and a low score here. And we found that the parameter has a very clear patterns. The bad samples always has a very small evaporation efficiency. So why was that? I think there may be two ways. One, to influence the interaction between the convection and the large scale circulations. One is a Kelvin wave that induced the Ackermann divergence over the West Pacific, and another is moist entropy advections. Because we have a very small evaporation coefficient, so our boundary layer is very dry, like we're showing here in red. It is the bad samples. Because our boundary is drier, so the convection will be suppressed and the precipitation will be very low. So in the mean state, the gradient of the moisture at 700 millibar from the West Pacific and to the Central Pacific is very low. That will introduce a very small and very weak moist entropy advection, a normalized drive downward motion, and therefore suppress the local convection and the constraint of the MSE budget. So we have a very weak.
I'm just going to ask you to move to your summary slide.
Okay.
You're there.
So here's our conclusion.
Very good.
So
if you just leave those there for us, Zhun, we can read those. But there are no questions in the chat yet. We have very little time, but I would like to ask, with your maps, which are really important for understanding the impact of regional causes of uncertainty, did you emulate in each of your model grid boxes?
Oh, could you please say again? Sorry.
You showed some maps of the causes of uncertainty.
Yeah.
And I'm wondering if you created emulators in each of those grid boxes to do your sensitivity analysis.
Yes. Yes,
we do that very often, but it's really powerful visually. Yeah. Okay, Zhun, that's fantastic. And do your results feed through into model development, or are they more about understanding the causes of uncertainty? Ben is asking.
Okay. What? Can you say again? Sorry.
You're going to have to answer in the Etherpad, I'm afraid, because we are out of time. So I'd like to welcome Saloua, if you're still with us here, to share your screen. You can turn your camera on if you want to.
Yeah, hello. Can you see my slides?
That's perfect, Saloua.
Yes, so my name is Saloua and I'm a PhD student at Surfax. I'm working with Ben Sanderson and Laurent Terré on the PPE of the atmospheric component of the CNRM model. So here is the summary of our PPE. So the goal here was to explore the parametric uncertainty of the climate feedbacks in the model. So we are using Arpège Climat 6.3, which is the atmospheric model in the global climate model of CNRM. We perturbed 30 parameters and we have a really small size of ensemble right now. We have 100 simulations, but we are planning on expanding it. And we are perturbing parameters from the convective turbulence, cloud microphysics, and radiation cloud processes schemes. The frequency of the data is monthly, and we have 3 years of simulation length. We are doing two kinds of experiments, one AMIP, which is SST prescribed between 1979 and 1981, and the AMIP Future 4K experiment, where we have a pattern warming of the SST for global warming of +4 Kelvin. So as I said, the goal here was to kind of explore the range of the plausible climate feedbacks and climate sensitivity we could have. And we tried to develop a method to find plausible alternative model versions with different feedback parameter lambda. So just a quick reminder of what is this feedback parameter lambda. So if we consider an experiment where we double the CO2 concentration, we will have a energetic imbalance at the top of atmosphere N, and if we let the simulation equilibrate, we have the ECS, which is the equilibrium climate sensitivity, and it is sensibility. It is the warming of the global surface temperature in response to the double of CO2 concentration, and lambda is the slope of this supposed linear relationship. So of course, this vision has a lot of flaws, but it's widely used. And here we estimate lambda from our two experiments. We take the difference between the AMIP and the AMIP Future 4K experiments in terms of the top of atmosphere radiative budget and the global surface temperature, and lambda is the ratio of these two changes. It can also be seen as the sum of all the individual feedback processes. And here is the distribution of this lambda within our PPE in blue. And as you can see, the range of the lambda values we have is wider than the range in 7 SEMIP6 models we took. So we took models that did the AMIP Future 4K experiments. And here the dashed black line is the reference model version. So it's the model calibrated with the reference calibrations as we have it in SEMIP6. So we have this broad range of lambda values, but not all of these simulations are plausible. So the question was, can we find plausible alternative model versions with a different lambda value? And to do that, we had to use a performance metric, and we started quite simple with only 4 variables. We looked at the long wave and short wave flux at the top of atmosphere, the surface temperature, and the precipitation. We looked only at annual mean averaged over the whole 3 years of the simulations, and we considered anomalies by removing the PPE mean. And we did EUF analysis of these anomalies across the PPE that we truncated at the 5th mode. We projected the observation onto this EUF basis, and we could have a kind of EUF-based RMSE, where we took the RMSE between the reconstructed 3D fields of the model calibrated with a given theta, and the reconstructed 3D fields of the observations. So we did that individually for each one of the 4 variables, and we aggregated these metrics just doing mean standardized with the error of the reference model, which is the model with the reference calibrations. We didn't weighted the mean, it's just right now it's just a mean. So now we have our PPE members, here the black dots, and they have each a performance metric and value of their feedback parameter lambda. So here's the performance metric is an error. So the lower it is, the better the model is. And the dashed lines cross here at the reference model. So as you can see, none of the members we have in our PPE do better than the reference model, but some of them are really close and show different lambda. So we wanted to explore better the parameter space. So we had to use emulators. And here it's just a simple multiple linear regression that allows us to predict from the 30 parameter values, the value of the 5 principal components of the EOF that allows us to recreate the error metric. And we also predict with another multiple linear regression directly the lambda value. So the gray dots here are 100,000 emulated points that are from a Lighten hypercube sampling of the parameter space. And it suggested that some of the calibrations could have a lower error than the reference version, but it's mostly shows that we can have a broad range of lambda value with comparable performance than the reference, and we wanted to explore that. So we did an optimization of this kind of problem. So we considered some different beans of the lambda range here, and for each one of the beans, we were looking for the best calibration we can achieve, meaning we minimized the ETOT with a constraint on the lambda value.
6 minutes.
Yeah. So here are the results with the emulations. So the gray line is the emulations, and we wanted to try that in the real model. So we sampled this line with these disks here, and we tried this calibration with our atmospheric model. And here are the results. So the blue line is the gray line I was showing earlier, and the triangles are the actual atmospheric run that we've calibrated with the calibrations we identified earlier. So these are our optimal candidates. And as you see, none of them are better than the reference, but some of them are really close. And the green area here is the plus and minus 1 standard deviation of the 7 CMIP6 models I considered. And we have 15 models here that are within this tolerance, showing a broad range of lambda. So the estimated ECS is here is from 4.1 to 6.1 Kelvin. So maybe I'll just leave up the conclusions here. But one important point is that we didn't constrain directly the top of atmosphere relative balance. So not all of our candidates are equilibrated. Actually, the one with the highest ECS are strongly unbalanced at the top of atmosphere. So this is a major perspective for the study. We want to find a way to constrain better this relative balance. And the method is published in a paper in GRL that is referenced here. And yeah, I'll take any questions. Thank you.
Very nice, Saloua. Thank you. I don't see any hands up yet or any comments in the chat.
I could ask a question if I may.
Go ahead.
That's very nice, Saloua. I wonder, in relation to what I showed that the model can be skillful at one thing, but not everything at once. Have you explored when is your model ever skillful against one thing and then bad against something else? And then when you try and get good skill against the other thing, it's then bad against the previous thing. How did you?
Yeah, we have that also. So we have, I think I have yeah. So here is actually the results for the individual metrics. So we can see that the black line here is the optimization line when you optimize on this aggregated multivariate metric, but you can optimize on one individual metric, of course, and yeah, the model are not performing the best in all the individual metrics. And actually, here we had some PPE members that were really good at long wave, and we kind of lose them. This is not the best figure maybe, but yeah, we have some biases in the long wave and in the precipitation in the optimal members. Even though they are doing really quite good in the multivariate metric, and it's super hard to find a metric to do the optimization without this kind of trade-off that we always have. And yeah.
I think that's one thing we should discuss maybe here and beyond, how we learn from these trade-offs that are being made about what the structural errors might be that are causing that to be the case.
Yeah.
I think we're struggling with that Leighton showed yesterday. But okay, I'll leave it there. Thanks a lot.
Thank you very much, Saloua. If you could stop sharing now, we're going to move on to our last speaker for this session, which is Yoko Tsushima. Yoko, you can share when you're ready.
Okay, yeah, thank you. I slightly modify the title on how to reconcile with structural errors in sensitivity to cloud controlling factors in HATGEM3. And the background is that climate sensitivity was a big uncertainty for many years, but it was assessed in recent years in IPCC, for example. And our model is known to perform the representation of the present day fairly well according to various assessments. But the climate sensitivity assessment showed that our model's sensitivity is outside of the range of 5 to 95 percentile range. And so it is a big problem for us. And in the meantime, with the ridge regression method, Zeppi and Nowak demonstrated that cloud sensitivities to various controlling factors, and we call this C factors from here, using the present day sensitivity can predict cloud feedback in global warming in the future. So this is very powerful diagnostics and assess. And so a summary of the talk as requested. So we are going to analyze the sensitivity to these cloud controlling factors using the GA8 PPE. And the result indicates that we have a problem in representing the seasonal variation of low to middle level cloud vertical development. And perturbing parameters could improve the sensitivities and climate feedback, but that could come with deterioration of some variables because the error is structural. So the improvement is a priority in model development. But in the meantime, since the range of climate sensitivity is constrained, a way for the PPEs, especially for the regional predictions, the usage of time-size atmospheric experiments with a range of SST could be a way. This is just a proposal. So our PPE summarizes like this. We use 71 parameter, 503 simulations, and we perturb various process parameters. And our simulation length is 5 years. And please see the details later. And just, I would like to briefly introduce the cloud controlling factor concept. So not just for the future, but for the present day, any cloud feedback perturbation with global mean surface temperature can be broken down into the contribution from controlling factors. They are typically surface temperature, inversion strength, relative humidity, and ascent motion, and upper tropospheric relative humidity. But here we focus on surface temperature and EIS estimated inversion strength because they are the dominant factors in global warming. And we use these observational data set. Here is a summary of the sensitivities of net cloud radiative effect, where we normalize the solar insolation to annually normalize. I skipped the reason for that. And the top panel shows the sensitivity of that variable to surface temperature from the observation left column, middle in the ensemble mean from the GA8 PPE, and the right column from the difference of the model. And the reason why we show the ensemble mean is that by taking the mean errors, we can show the common structural errors among the PPEs. And what we can see is that the remarkably special pattern of the very well represented in these ensembles. However, if you look at the difference, you can see that the cloud in the mid-latitude zones, typically the extratropical cyclone regions, are too positive, which means that it is too sensitive to be surface temperature increase. And similarly, the sensitivity to EIS, the bottom panel, the spatial pattern are well represented, but if you look at the spatial pattern, you also see some differences. And note that EIS used to be used over ocean, so there is some noise in the land, but these data are all used as a NOAC analysis. And so we apply this analysis to ISIC clouds. And here I show the highlights that we noticed that the response of middle clouds. So the left column shows the middle thin clouds, and the middle column shows the medium thickness middle clouds. And the right column shows the middle with thick cloud categories. And the top panel shows the PPE, and the bottom panel shows the observations. And it clearly shows that the biggest disagreement exists in mid-latitude, in mid-level clouds. And a reduction of the mid-level clouds over the mid-latitude area are quite remarkable. And also we can see similar reduction in the stratocumulus region, for example, in the medium thickness clouds and thick categories.
6 minutes, Yoko.
Okay, thank you. And as it's expected that the relationship of the performance of this sensitivity in middle clouds are strongly linked to global feedback, especially for middle thickness clouds in the top panel. So the improvement of the sensitivity in middle thick cloud seems to be promising. But how we do that? And I have to skip these figures, but the regional analysis with some parameters implies that the highlight that we have problems in representing the migration of the low to mid-level clouds from winter time to summertime. And we found that there are different parameters involved in different seasons in the bottom panels. The different color shows different parameters. So there seems to be a way to improve this sensitivity by changing parameters. But what will happen if we improve that sensitivity? What will happen to that overall performance of the present day? So this figure shows the RMS error of the performance of the blue dots for all ensemble members and orange dots for the top 10% performers with regard to the middle thick clouds sensitivities. And this figure highlights that overall, the top 10% models tend to have members which have a better performance than the standard ones, which is red marks. But we have some deterioration. For example, in a thick cloud, we have a big reduction in and better performance in the top 10% models, but it does not necessarily come with the improvement in the medium thickness category in the square box. And also we have slightly have to miss the best performer in precipitation and also long wave cloud radiative effect and surface air temperature and 200 hectopascal zonal wind here. So I'd like to go to summary so that this controlling factor analysis is a powerful way to identify the problem in a model. And from model development perspective, this is a priority to have a model which has a good climate response representation. Having said that, since we already have climate sensitivity range is constrained, so a wide group of PPE users for regional predictions, ensemble members which are chosen by focusing on the performance which are important for that community, for example, spatial distribution or representation extremes, and then conduct the atmospheric experiment with a range of SST increase could be a way. That's my proposal. Thank you.
Thank you very much, Yoko. Are there any questions for Yoko? If not, maybe it will feed into our discussion, Yoko, because I think we're going to speak about structural errors and how we identify them and what the implications are. So one thing that stands out to me immediately, if you'd like to stop sharing, is that,
okay.
Thank you. When there are structural errors in the way you've identified, whether that means the model should be tuned differently for summer and winter to capture those transitions. And if that means we should have more fidelity in some process that's related to those transitions, so they're represented more accurately according to those different environmental conditions, or if there's some better way of handling that without increasing model complexity.
Yeah, so clearly that if we want everything to be improved, that just parameter tuning is a rather short-term solution. But we have limited time, and we need some model which has a good representation, and the good representation depends on the needs which we know. And here I noticed some how much you consider climate sensitivity or feedback as a factor of the good model is a good question to consider, especially for the community who want to use that simulation for regional prediction, especially because that the good performer of the climate sensitivity model, if you look at, does not necessarily have a good spatial distribution of the, does not promise the good spatial distribution. So you need to really think what is important.
There's a lot to unpack there. I'll let you take over, Ben.
So thank you so to Yoko and all the speakers this morning or this afternoon, depending on your time zone. It's been really interesting to see that cross spectrum of talks and perspectives and people using PPE. So a big thank you for all our speakers this morning. We have 40 minutes left for discussion, and we've the way we formatted the workshop was we've only given our speakers 10 minutes each. And so we've really curtailed questions and discussion around talks. If there are any questions you would like to raise about what you've heard so far this morning, then now is an excellent time to raise them. So either raise your hand or put them in the chat. And likewise, if the kind of results we've seen this morning have spurred any thoughts about your own work, you're very welcome to share a slide or a figure. So again, raise your hand, and we'll try and involve you. So I'm just going to pause for a few minutes to give you an opportunity to do that. So I'll also note that there's lots of really excellent discussion that's been going on in the effort pad. So there's a link to that from your program. And at the very bottom of the effort pad, there are a section for comments on the final discussion. So feel free to raise your hand. Feel free to put a question directly in the Zoom chat, but also feel free to put some points in that final discussion. So Ken, I think you've got a point. So over to you.
Yeah, I had a general question for everyone this morning, and most people showed it in some form that we have this compensating error problem, that we're perturbing so many things, and finding that there are many essentially parameter combinations or model variants that agree with the observations. And then you have to select a few of those sometimes in the climate modeling world, which you're then going to run in coupled modes, but you're only picking from all the equally plausible parameter combinations. And whether anyone's thought more about how to narrow that down a bit, how do we overcome some of this cancelling error problem? I mean, in principle, if you could design a field experiment to measure a particular parameter, so for example, if deposition is your thing that's compensating with emissions in our world of aerosol, you would go out and try to deliberately measure aerosol in a condition where deposition was the dominant process. Then you wouldn't have error compensation. So you could tackle it like that, but I just wondered if anyone had thought more about how we can make progress with this, because I don't think it's good that we have huge combinations of parameters across diverse parameter space that give apparently equally skillful models, because when you run them forwards, they turn out not to be equally similar. So for us in the aerosol forcing world, the forcing can be hugely different for simulations that look apparently the same compared against present observations. And I think that will be the same for the chemistry, the climate, etc. So I think that's a big topic, this equifinality or compensating error. Has anyone thought any more about making progress with that?
Ken, can I make a point? Sorry, we haven't got a camera set up at the moment. Well, we've got John Rostrom instead of me, which is probably better.
That'll do.
But I do wonder to what extent that point is about how many things you're using to look at your model. If you just look at one variable, then you're going to find there's lots of ways of making that variable look like, like a certain value. But if you break it down by looking at more and more variables, I think you do end up kind of making the members look more different from each other. There's more ways to discern the differences between the members. So I do wonder sometimes whether that's part of the reason why they don't look different if you just look at one thing, but they create different predictions in the future.
Yeah, I see what you're saying. You throw more variables at it to try and constrain it. And I think we've done that in the aerosol world. And I think the problem is that each of these aerosol variables actually is sensitive to rather similar sets of parameters. So you end up finding the same thing over and over. You constrain the same thing over and over. So you end up with pretty much the same degree of equifinality, no matter what you throw at it.
I think there might be a difference between, like, if you're looking at something that's more closely, the variables that you look at are probably more closely related to the parameters that you perturbed, whereas I guess I'm more used to looking at the kind of things that Yoko had on her last slide, which are kind of big kind of variables across the globe, and they're kind of, there's more emergence, there's more processes interacting, and so they're further downstream, I think, from the parameters. So that may also factor into exactly how you see that. Also, if you do look at more variables, then it better exposes the structural errors, so that, you know, sometimes for one variable, the observations can sit inside the distribution, but we had examples yesterday when we went to 2 variables where the observations were outside the cloud, but within each marginal distribution, they would have been inside. So adding more variables also exposes more structural error, and that would flatten out the constraint or make it difficult to include all the observations in the constraint. So there's a trade-off between all that as well.
So we've got raised hands from Christiana and Ulrika. Are you raising about this discussion point, or is it a what? So Christiana, do you want to go first?
Yeah, I was just going to say, I think when it comes down to how do you determine between these like equally possible parameter combinations, it does make a lot of sense to really try and target our observations. So it's not just about finding what observations have already been made and what they constrain, but actually which locations, which co-located observations would hit exactly that bit of the parameter space that could tell between these different parameter combinations. We know that a lot of observations can be recreated in many, many different ways, but there are certain sort of phenomena, certain locations in the atmosphere where this is not the case. And that surely is a really powerful way to constrain it, just going out and making intentionally the right combination of observations to hit at determining between the different model variants.
So the floor's yours, Ulrika, if you want to ask your question or make your comment.
Yeah, I just wanted to say, I mean, it's maybe obvious from my presentation, but there's the one way is to sort of tackle the observations, but the other way would also be to reduce the amount of processes, right? I mean, if you have an underdetermined model that you build, you can either try to get more determinants in, or you can try to reduce this. And this would be an interesting question. How many parameters do you need to fulfill what the observations already show? And I mean, some people presented something that means there would be less parameters or fewer parameters that we need, but then others also show these structural problems we already run into. So for me, it's not even clear whether we have too many or too few. It seems to be different depending on what you look at.
Yeah, I absolutely agree. I think you're mainly the only person who's talked about simplification, and a lot of us have talked about models that are underdetermined, and so we need to meet somewhere. We can't keep adding complexity to models and say we're underdetermined. And from all this we know from PPEs, we might be taking the wrong approach. Maybe you're right. We have to simplify. I think we need to have that discussion. Others would argue we'll lose fidelity if we do that. So there's this tension between fidelity and reliability. I can't get my head around. But I think we need to expand that discussion somehow.
Yeah, exactly. Because I mean, what is fidelity worth if it's unconstrained, right?
Yeah, exactly. So this is a point we need to make in the summary paper, that we need to be aware of this sweet spot. It's not far right towards complexity, and it's not far left towards simplification. It's somewhere in the middle, and the PPEs can help us with that. Good point. Yeah.
So there's a really nice discussion on the FAPAD of that point that was just made about on the discussion of Ken's talk. But I agree, it'd be a great point to pick up in the discussion paper. It's probably worth mentioning at this point that in terms of outcomes from this meeting, we'd like to write up a perspective piece. So later on, Ken might say a bit more about that. But the other outcomes is there interest within this community in meeting more regularly, either as maybe a yearly meeting in this kind of format, or as a seminar series that we could do monthly or bi-month or every 2 months, where we give more time for individuals to go over their work and get feedback from our peers. So if there are any thoughts on that, then feel free to raise them. So there's the discussion's already touched on it already. There's a lot of discussion this morning about structural errors. We discussed it a lot yesterday as well. It came up So in Ken's talk, in Zhun Guo's talk, looking at the variability, the PPE was unable to capture the reanalysis in some phases of that variability. In Saloua's talk, kind of really illustrated this, and Yoko's as well, about how the PPEs are perhaps well placed to expose models' structural limitations. And part of the discussion yesterday was that much of the perception outside our communities is that you use multi-models to look at structural differences, and put a parameter on some models to look at parameter sensitivities within a model structure. But the discussion yesterday, one of the emerging themes was that we had a sense that maybe the PPEs are uniquely placed to inform and expose structural limitations of our models. And I wonder if there's any discussion we want to make about that now. Anyone want to make any points along those lines?
Sorry, Ben.
So go ahead, David.
So is this a good time to be able to share a plot?
Yes.
Based on the chat that Ken and I were having yesterday. Wait a minute. Window. Bear with me. There it is. So I take it you can see that now. Can you see that?
Yes.
So that's your plot, yeah, Ben?
Yes.
So can you see the cursor move?
Yes.
Cool. So these are, for the people who weren't there yesterday, this is one of the Sherwood et al. Indices on lower tropospheric mixing, and this is the climate feedback estimated from AMIP and AMIP future runs. And the red cloud is our 7th atmospheric version configuration, and then the blue is the 8th and the green is the 9th. So we've got successive PPEs. And one thing that Leighton and Jill mentioned was that they can't use some observations to constrain because there's complete lack of overlap, there's inconsistency, big structural errors. And so that deals with the kind of historical aspect of structural uncertainty. But Ken and I were kind of talking about the fact that we were talking about constraints within one PPE. Then, so you're trying to constrain, you're trying to use a variable like this to constrain feedback, then you can get a constraint within that PPE. But if you then fixed what was ever causing that structural errors of that model, then I was arguing that that actually might change where the feedback goes. It doesn't just shift the x-axis here, it could also shift the y-axis. And that when we do constraints, we need to capture that kind of future structural uncertainty in there. And in some of the PDF methods that I've done and with UK's climate projections, we have a term to capture that. And I thought this plot kind of illustrated it quite nicely, because I don't know where the observational constraint here is. I'm not even sure.
It's around 0.5. It's
around 0.5, okay. So, so that's interesting. Can we make it 0.4?
Okay.
So if we did constrain around here with the original curve, we would probably end up with a full range anywhere between -1 and -1.8, because really it's the interaction between the observation and the structural limitation of that red ensemble. But when we basically changed the entrainment scheme in the model from the red curve, which was kind of a prescribed value for deep entrainment, to what we call a prognostic entrainment scheme, which relies on recent amount of convective rainfall, then it shifted towards the blue cloud, and then they've later consolidated and shifted further to the green. So they're quite small changes actually to the model, but they've shifted the whole cloud. And if we were constraining again, we would have shifted our feedback outside the range considered by the red. So my point was that when we're constraining on PPEs, we do need to consider, I think, what
the fact that if you did fix the problem, which was causing the structural constraint, you might shift the whole cloud. And I thought this diagram showed it really nicely. Ken, do you agree?
Yeah, I agree. That's really good. That's really nice figure. It does illustrate a big problem that maybe we haven't grappled with here, but I think we need to, is, yeah, consistency of constraint across model versions as you evolve the model. Yeah, does the constraint that you applied, all that work you did with the PPE of your GA7, is that all for nothing when you move to GA8? I mean, maybe that's the way we do model development, is not linked to PPEs. If we could tie model development more to what we're really learning from PPEs, more targeted, maybe this problem wouldn't be so bad. Maybe that's a pipe dream.
I also wonder whether this was like advocacy for that, the idea of like adding more and more PPEs. So imagine if CNRM was here and F goals was here, and the other models we've heard about from like CAM PPE, and you know, maybe the PPEs are only filling like part of a space, and so you need quite a few of them. And of course, the same applies to the multi-model ensemble as well. You know, each of those multi-model ensemble members could have a PPE around it. A point you made loads of times, Ken.
Yeah, you're right. In CMIP, of course, you don't have a whole two-dimensional PDF on that figure. You have a point.
Yeah.
And you know, it's just not enough information, is it? This is what we're arguing. If every group did some form of PPE, we would have whole PDFs from all the models, and we'd learn a lot more about the causes of disagreement, etc., rather than just having one realization from that model. So that's something we need to push for, I think.
I'm going to stop sharing. Thanks for that.
So we have a question from yourself, Ulrika. I've lost the ability to speak.
No, I just wanted to ask whether I understood this correctly. So you said basically moving from red to green, or when you do the uncertainty estimate for the red one, you should already take into account what the future will bring to the green one when you change structure. But how do you know? It doesn't make sense.
So in the paper I tried to do that. What we did was we used we actually combined information from the other models from CMIP 3. Actually, it's SexNet out 2012, but we used other models and we tried to use our PPE to predict the other models. That gave us a prediction error in the future, and then we estimated from that the kind of typical error we would get. The thing that misses, and the thing we're always going to have a problem with in modeling, is it misses the systematic errors that were common to all the models across the PPE and the CMIP data I was using. So so there's I think some of us have some ideas about how you might try and get a glimpse of what impact fixing a structural error might do without actually finding the root cause in the code and the way you build the model. That there might be like, I don't know, Leighton has ideas, or I'd be interested to know whether the Hui Su's mechanical, I can't remember what it was called, but that method for taking stuff out. I do wonder if if there needs to be more ideas on trying to get an idea of the first order impact of trying to fix some of these things, like nudging experiments. If you know that the biases are causing the structural error, present day biases are causing the structural error, that kind of thing. But I don't know. It's pretty tricky.
Yeah. So did I understand you correctly? At the moment, you're taking model sort of inter-model disagreement as a proxy for how your own model will deviate in the future.
Kind of using out of sample models to estimate how well, just to add an extra uncertainty onto that, really. But it's not necessarily that, they could all be making the same mistake. So it could be.
Yeah, wrong. I was going to say you're basically guessing it will be similar orders of magnitude, but you don't really know.
Yeah, but it does widen the uncertainty, which.
Yes.
So that's an interesting thread, kind of, and it kind of makes you think about to what extent you can quantify that distance between your possible models, be they multi-models or PPE models, and the real world. So yesterday, Greg from showed that with the GIST model, in two-dimensional spaces that the observations fell outside the spread, and so you but it was in the marginal of each of the parameters in one dimension. I can't visually convey that. I didn't have this talk, but is that a good way of kind of expressing structural uncertainty, or are there other ways we should think about it?
I think it's potential structural error. It's, not necessarily. I think it needs more investigation, but it's a strong indication that there is. And I think there are other things we can do to look at structural error. I think what Leighton showed, where you try to constrain to one variable at a time and then show inconsistency with another one. And when there's strong inconsistency, you might get a clear indication of the cause of structural error thrown up by the inconsistencies, rather than just saying, you know, my compromise constraint doesn't look so good for various things. I think we can be more systematic about that. And I think there can also be things like, we have spatial patterns, we have temporal patterns. There's a lot more information in our models than just mean quantities. Maybe we can find fingerprints of potential structural error. So when there is a bias, where does the bias show up? When does it show up? There's a lot more we can do to investigate causes of potential structural error when we think we found them. I think that we have a proposal at the moment to do things like that, but it would be nice to develop more thinking more widely about how we go from thinking we have a structural error from a PPE to actually identifying what it might be.
I think just as an aside, I totally agree, Ken, but I think as an aside, it's important to clarify, we're discussing here the types of structural errors where you need different parameter combinations to match those different measurements or types of observation. Whereas there's other types of structural errors out there that we've detected where the observation is right outside of our PPE range, which suggests something more systematic that has to be approached in a different way. And we could maybe spend some time thinking about all sorts of different classifications of structural errors, which might crystallize our thinking about how to deal with them distinctly.
Yeah, that's a good point. And that comes back to Ben Sanderson's point yesterday that we need to actually define structural error.
He flagged 3 different types, but I think that could easily be expanded upon.
Yeah, I didn't actually agree with him, but we should have that discussion. And yeah, I like your idea of different types of structural error or how they manifest themselves in a PPE. Might be a good way to start.
So I'm aware that we've got just over 10 minutes left of the workshop. I wanted to pick up on another strand that kind of emerged yesterday about whether there is a potential to use to look at a multi-model approach to PPEs, and it feels like there's so yesterday the North Americans were involved in the session, and there's already a intercomparison of global atmospheric models amongst the 3 North American groups. So I guess Annika and Department of Energy. So today we've heard from Zhun Guo and Ben Wang about the TMIP and the AMIP runs, and we've heard from Saloua about the CNRS model, and we've heard from Yoko about today, and John Rostrom yesterday about how GEM runs. And it's a broader question, but I wondered whether, from a global atmospheric modeling perspective, whether there is an interest in intercomparing some of those AMIT runs and whether that might be a way forward.
Yeah, I do like the idea of multi-model PPEs because we talk about the structure difference, although I think it's not really clear what we mean structure differences. But if we have the multi-model PPEs, so especially I think similar types of PPEs like convective perturbations or cloud perturbations, then we might learn more just by comparing different model of PPEs, because like we said, if there are things actually outside the bound, actually compare different model may tell us the structural difference than confined to one model.
So I very much agree. I guess I mean, there are lots of strands here. One is do we understand enough about each other's ensembles to kind of see where those comparisons are meaningful? And I guess each of our talks has a breakdown, a definition of our PPA approaches, and that's a good start. And is there a willingness and an interest maybe in sharing those results? Sorry, Leighton, do you want to go?
I think we got the impression yesterday that there was quite a bit of enthusiasm for that idea. We were reaching consensus on that with some members of yesterday's group. There's definitely some discrepancies in terms of how our PPEs will be set up, in terms of sea surface temperature and whether they're nudged or not, what year of meteorology they're nudged to. So we just have to be transparent about those factors that will confound our understanding. And as well as John pointed out, with the different generations of PPEs that you guys have created, there'll be different parameters that are perturbed in each of those, depending on each person's or each group's priority. So essentially, each group would need to find, someone would need to raise a particular question that's tangential to what each group is creating their PPE for, and then each PPE group would have to mine that data and make it available, wouldn't they? So we had something to investigate collectively. I'm sure that's possible, but there's a lot to understand in terms of how the setups affect the output. But it would certainly be interesting work.
And we should remember there are already multi-model PPEs that have done the preparatory work, like what Oliver showed. They've done the preparatory work to perturb common parameters in these models. It's probably easier in the chemistry world than the climate world, but I think we can learn from what they have learned. I think certainly in any perspective paper, we should reflect on what can be learned from multi-model PPEs, and that might stimulate then more larger scale climate model PPEs, where we can really demonstrate that it's of high value. And now, Oliver, if you're still online, but I think that's a really good example where you designed it from the outset to be a multi-model.
Yeah, I think I'd see I'd be cautious about ensembles of opportunity, in that it's a problem of incommensurability. You're always kind of going to be comparing apples and oranges, and the question is what we can learn from that. Even if we're looking at different parts of the same parameter space, the advantage with the designing things from the scratch, of course, is that you really can try to be as comparable as possible. And I put in a vote for looking at pseudo parameters rather than parameters, in the sense of focusing on the processes rather than on individual technical parameters, because you're usually comparing models with different algorithms. But there's a lot to be learned from using kind of pseudo parameters where you're scaling a whole process, because then the individual model can go back and look at what parameters would be required in that model to affect the process. So I think there is a lot we can learn from that.
That's the same sort of methodology, Oliver, where you could actually make sure they're scaled to a similar degree, couldn't you? Mm-hmm. With the global mean metrics as a starting point.
That's what we decided to do in the aerosol, wasn't it? Because we, even at something as simpler as aerosol activation, there wasn't a common parameter. There was a common output process rate or something that could be perturbed. That's a really good point, Oliver. Thinking of if they were ever to be designed in future for climate models, that might be a better approach than actually the native parameterization parameters. Yeah.
So pragmatically, I imagine.
Like that. Sorry.
Sorry, no, good. Go for it.
Oh, I think I really like what Oliver said. I think instead of just focusing on particular model parameter, but instead of we can look at some process, a common process, then can derive from model outputs, then that we can compare across models. I do like that idea.
Or maybe that's a way to make them more comparable. Once you have perturbed sort of the native parameters, this will have an effect on the process rates. Maybe then we can normalize to process rates. So rather than, you perturb a whole bunch of things that end up perturbing the overall process rate, if that information has been stored, then you can now use it to sort of normalize to those, I think. Possibly.
That's a question.
Yes, just quickly to make the point that that Saloua showed something similar yesterday in the discussion. She compared HadGem and the CNRM model, and she looked at the various role of different processes, say boundary layer, deep convection, and so on. So maybe that's a nice example. So David, I think this is the last question before.
So it's not an additional point, actually. I was just thinking, yeah, Saloua has done one way of doing it, which is to group the parameters, and I think that's a really nice way of doing it. But I was just thinking, for a global model, it might be way more challenging to think of it in terms of processes than, say, a scheme, you know, or a model that's more focused on kind of set processes, like an aerosol model, maybe a chemistry model. I think for a global model, climate model, it's going to be really challenging to like understand what those processes are. We don't even do it the same in a lot of processes. You know, there must be processes in CNRM models that are just not even got an equivalent in HadGem 3, and vice versa. It's just not, they're just not built like that.
So before we wrap this up, I just want to briefly mention yesterday there's a lot of discussion about from the global atmospheric modeling community who are trying to run couple runs. So this is probably relevant to Saloua and Zhun Guo's work, and that those people who have tried it, so that's the GIST group and the Metofis group, have run into real challenges in terms of finding stable combinations of atmosphere and oceans. So that there's maybe an interest between those groups trying to do that in keeping in touch. So Zhun Guo and Saloua, if you're interested, we can talk about that offline. Before I pass over to Ken, I wondered whether we could have a group photograph. Do you think that's a good idea? Because we think this is a fantastic meeting and we don't have a visual reflection of that. I wondered if you were happy to, whether you could turn on your camera and we'll try and take a screen capture.
Go for it.
David's not shy of a camera. Did you see him race over there? And John ordered him off.
This was about, I think about a third of the number of people. We had about 65 yesterday, didn't we, at peak? So
that's right.
Nightmare, because I'm not allowed to come on video.
So unfortunately, the computer says no to my face appearing on this screen, which I just, I'm mortally offended by. It was a good meeting up until this point.
Squeeze in next to John, David. You were fine there.
But John's.
I'm not on the first page on your screen.
I'll tell you, I might leave, and then maybe John will appear.
Oh, there we go. Yeah, you can join now, David.
Okay, if everybody is ready, I'll take a picture with those who are up. So smile, please. Great. So thank you very much for that. I'll pass you back to Ken.
Okay, yeah, thanks, Ben. And thanks, everyone. I think yesterday and today they've been different, but they've been really stimulating. Actually, it exceeded my expectations. I wasn't sure whether there was such a thing as a PPE community. But it seems there is. I think a lot of shared interest and a lot to learn. I would be really interested actually in feedback, what people learned from this, about how they might shape their own work. It's something we hope would come out of this meeting. Maybe, I don't know whether we can create a form or something to just jot down the key things you learned. So just to finally mention, the recording will be available. WCRP will make that available to us, hopefully then on the YouTube channel. We do intend to write a perspective paper, and what we'll do, I think, is send out a skeleton of the main discussion points there and the points we want to be able to convey to the community, which is not our community, it's the wider community who think PPE is personal protective equipment. You know, we need to convince them what we can do with PPEs, and it should be a key part of for example, CMIP maybe in future. So we'll write an outline of that and then ask for your input. I think everyone should have the chance to comment on and contribute to that. Yeah, it looks like there'll be other follow-up papers maybe on PPEs of opportunity, etc., which would be another good outcome of this. And I know, Nico, you're encouraging us to talk to CMIP, whoever CMIP is, particularly the ocean community, because of this flow of going from atmospheric PPE to coupled PPE is really important to get right if we were to learn about climate. So we'll certainly do that. Yeah, Nico, I don't know, did you want to make any other final points from a WCRP perspective?
Guys, I was at the very beginning of the meeting today, I was mentioning to Leighton and Ken, with all the online webinars, workshops, meetings that I have attended for the last 2 years or so. To be fair, this has been one of the most valuable in the sense that it was well run. I mean, 8-minute presentation, and it's very easy to run over time very quickly. And the discussion was great in that sense. Ken mentioned yesterday, perhaps because it is a community that you guys understand each other, right? And then it is how the discussion and the science is evolving. Certainly there are challenges, and like Ken was saying, certainly I think it will be important to have some discussion with the WCRP working group on couple modeling, which is the working group responsible for CMIP and the CMIP panel. They are in preparations for CMIP 7 already. So I think that will be an important and timely discussion to have. The WCM is meeting in 3 weeks in Boulder. So there will be a good opportunity for that. And I'd like to thank Ken, Leighton, and Ben for pulling this together, and it was great. And I'm glad that WCRP would be able to support and have this meeting online. Hopefully next time. When is that you said again? 1.5 years in 18 months. So
yeah, I think probably. I mean, I don't know where 1.5 years came from, but I think probably 1 year. But yeah, I think I probably don't need to ask. I think there would be enough enthusiasm based on what we've been discussing here for another meeting like that.
Right. And hopefully in person, right? I think that would be fantastic. And for all those who are attending the workshop yesterday and today, guys, thank you very much. It was great, and looking forward for all the outcomes and further discussions.
Thank you.
Thanks to Nico from essentially sponsoring the meeting and getting it out there to people. It's good to have that framework. Certainly raises the profile of a meeting to have your contribution, and anything we write as well will carry more weight if we're doing it within WCRP.
Can I just raise one more point before we move on and wrap up? Would be that there's been some interest in having more regular meetings, there's more regular seminar series perhaps. So I think maybe on our form that we send out to participants, we could get you to fill in if you're interested in taking part in that, and maybe some early career researchers want to help set that up. That could be really stimulating to bring our community closer together.
Okay, great. Then I think we're done. Hope we meet everyone again, maybe face to face. But yeah, look out for information coming probably from Leighton on next steps. Thanks, Leighton, for being so efficient in organizing. You really did it. So thanks very much for that.
Thanks, everyone.
Great. Thanks all.
Thanks, everyone.
Bye.
Cheers. Thanks.
Thanks very much.